Nimm is a mathematical game of strategy in which two players take turns removing objects from distinct heaps. On each turn, a player must remove at least one object, and may remove any number of objects provided they all come from the same heap. Variants of nimm have been played since ancient times. The game is said to have originated in China. It closely resembles the Chinese game of Tsyan-shizi, or picking stones. But the origin is uncertain. The earliest European references to nimm are from the beginning of the 16th century. Its current name was coined by Charles L. Bouton of Harvard University, who also developed the complete theory of the game in 1901, but the origins of the name were never fully explained. The name is probably derived from German nimm, meaning take, imperative, or the obsolete English verb nimm of the same meaning. Nimm can be played as a Misere game, in which the player to take the last object loses. Nimm can also be played as a normal play game, which means that the person who makes the last move wins. This is called normal play because most games follow this convention, even though nimm usually does not. Normal play nimm is fundamental to the Sprague-Grandi theorem, which essentially says that in normal play every impartial game is equivalent to a nimm heap that yields the same outcome when played in parallel with other normal play impartial games. While all normal play impartial games can be assigned a nimm value, that is not the case under the Misere convention. Only tame games can be played using the same strategy as Misere nimm. A version of nimm is played and has symbolic importance in the French New Wave film Last Year at Marienbad. At the 1940 New York World's Fair, Westinghouse displayed a machine, the Nimmatron, that played nimm. It was also one of the first ever electronic computerized games. Herbert Koppel, Eugene Grant and Howard Baylor, engineers from the W.L. Maxon Corporation, developed a machine weighing 50 pounds which played nimm against a human opponent and regularly won. A nimm playing machine has been described made from Tinker Toy. Nimm is a special case of a percent game where the percent consists of disjoint chains. Gameplay and illustration. The normal game is between two players and played with three heaps of any number of objects. The two players alternate taking any number of objects from any single one of the heaps. The goal is to be the last to take an object. In Misere play, the goal is instead to ensure that the opponent is forced to take the last remaining object. The following example game is played between fictional players Bob and Alice who start with heaps of 3, 4 and 5 objects. Sizes of heaps moves, ABC. 3 4 5 Bob takes 2 from A, 1 4 5 Alice takes 3 from C, 1 4 2 Bob takes 1 from B, 1 3 2 Alice takes 1 from B, 1 2 2 Bob takes entire A heap, leaving 2 2s. 0 2 2 Alice takes 1 from B, 0 1 2 Bob takes 1 from C leaving 2 1s, 0 1 1 Alice takes 1 from B, 0 0 1 Bob takes entire C heap and wins. Mathematical theory. Nimm has been mathematically solved for any number of initial heaps and objects, and there is an easily calculated way to determine which player will win and what winning moves are open to that player. In a game that starts with heaps of 3, 4, and 5, the first player will win with optimal play, whether the Misere or normal play convention is followed. The key to the theory of the game is the binary digital sum of the heap sizes, that is, the sum neglecting all carries from one digit to another. This operation is also known as exclusive OR vector addition over GF, 2. Within combinatorial game theory it is usually called the nimm sum, as it will be called here. The nimm sum of x and y is written x-y to distinguish it from the ordinary sum, x plus y. An example of the calculation with heaps of size 3, 4, and 5 is as follows. Binary decimal. 0112 310 heap A, 1002 410 heap B, 1012 510 heap C, 0102 210. The nimm sum of heaps A, B, and C, 3-4-5 equals 2. An equivalent procedure, which is often easier to perform mentally, is to express the heap sizes as sums of distinct powers of 2, cancel pairs of equal powers, and then add what's left. 3 equals 0 plus 2 plus 1 equals 2 1 heap A, 4 equals 4 plus 0 equals 4 heap B, 5 equals 4 plus 0 plus 1 equals 4 1 heap C, 2 equals 2 what's left after cancelling 1s and 4s. In normal play, the winning strategy is to finish every move with a nimm sum of 0. This is always possible if the nimm sum is not 0 before the move. If the nimm sum is 0, then the next player will lose if the other player does not make a mistake. To find out which move to make, let x be the nimm sum of all the heap sizes. Take the nimm sum of each of the heap sizes with x, and find a heap whose size decreases. The winning strategy is to play in such a heap, reducing that heap to the nimm sum of its original size with x. In the example above, taking the nimm sum of the sizes is x equals 3 4 5 equals 2. The nimm sums of the heap sizes a equals 3, b equals 4, and c equals 5 with x equals 2 are, a x equals 3 2 equals 1, since equals 001, b x equals 4 2 equals 6, c x equals 5 2 equals 7, the only heap that is reduced is heap A, so the winning move is to reduce the size of heap A to 1. As a particular simple case, if there are only 2 heaps left, the strategy is to reduce the number of objects in the bigger heap to make the heaps equal. After that, no matter what move your opponent makes, you can make the same move on the other heap, guaranteeing that you take the last object. When played as a Misere game, nimm strategy is different only when the normal play move would leave no heap of size 2 or larger. In that case, the correct move is to leave an odd number of heaps of size 1. In a Misere game with heaps of sizes 3, 4 and 5, the strategy would be applied like this. A BC nimm sum. 3450102 equals 210. I take 2 from A, leaving a sum of 000, so I will win. 1450002 equals 010. You take 2 from C. 1431102 equals 610. I take 2 from B. 123002 equals 010. You take 1 from C. 12200012 equals 110. I take 1 from A. 022002 equals 010. You take 1 from C. 02101112 equals 310. The normal play strategy would be to take 1 from B, leaving an even number, heaps of size 1. For Misere play, I take the entire B heap, to leave an odd number of heaps of size 1. 00100012 equals 110. You take 1 from C, and lose. The previous strategy for a Misere game can be easily implemented. Proof of the winning formula. The soundness of the optimal strategy described above was demonstrated by C. Bouton. Theorem. In a normal nimm game, the player making the first move has a winning strategy if and only if the nimm sum of the sizes of the heaps is non-zero. Otherwise, the second player has a winning strategy. Proof. Notice that the nimm sum obeys the usual associative and commutative laws of addition and also satisfies an additional property, x equals 0. Let x1, xn be the sizes of the heaps before a move, and y1 and the corresponding sizes after a move. Let s equals x1 xn and t equals y1 n. If the move was in heap k, we have xi equals y for all ia permil k, and xk. By the properties of mentioned above, we have t equals 0 t equals s t equals s equals s equals s 0 0 0 0 equals s xk t equals s xk. The theorem follows by induction on the length of the game from these two lemmas. Lemma 1. If s equals 0, then ta permil 0 no matter what move is made. Proof. If there is no possible move, then the lemma is vacuously true. Otherwise, any move in heap k will produce t equals xk from. This number is non-zero, since xk are permilic. Lemma 2. If sa permil 0, it is possible to make a move so that t equals 0. Proof. Let d be the position of the leftmost non-zero bit in the binary representation of s, and choose k such that the dth bit of xk is also non-zero. Then letting x equals s xk, we claim that x0 all the move must result in non-negative coordinates, and if a player reduces the point to the other player who cannot make a move loses. thus is a winning position. Similarly, it can be demonstrated that 3, 5 are winning positions. Since can be reduced only to 1, 0, each of which can be reduced to hence the player who makes move on loses and hence is a winning position for the other player. Planar nimm was proposed by Boris Verkhovsky, who also showed that the winning strategies of a planar game are determined by a system of equations with two unknown integer sequences and formulated an O-log n algorithm for computing winning states less than n. See also, Dr. Nimm fuzzy game, Nimba, Nimrod, octal games, star, subtract a square, zero game, Android nimm, Raymond Redeffer, last year at Marienbad. References. Additional reading, W. W. Rouse Ball, Mathematical Recreations and Essays, The Macmillan Company, 1947. John D. Beasley, The Mathematics of Games, Oxford University Press, 1989. Elwin Berlekamp, John H. Conway, and Richard K. Guy, Winning Ways for Your Mathematical Plays, Academic Press, Incorporated, 1982. Manfred Eigen and Ruth Ilde Winkler, Laws of the Game, Princeton University Press, 1981. Walter F. Fuchs, Computers Information Theory and Cybernetics, Rupert Hart Davis Educational Publications, 1971. G. H. Hardy and E. M. Wright, An Introduction to the Theory of Numbers, Oxford University Press, 1979. Edward Kussner and James Newman, Mathematics and the Imagination, Simon & Schuster, 1940. M. Kachik, Mathematical Recreations, W. W. Norton, 1942. Donald D. Spencer, Game Playing with Computers, Hayden Book Company, Incorporated, 1968. External links, £50 Computer Plays Nimm. The New Yorker Magazine Talk of the Town, August, 1952, The Hot Game of Nimm. Nimm Theory and Connections with Other Games at Cut the Knot, Nimm and Two-Dimensional Super Nimm at Cut the Knot, The Game of Nimm at sputsoft.com, Nimm on NCTM's Illuminations, NIM and Excel spreadsheet using basic formulas to determine best moves for a 3, 4, 5 start point. MindNimmer, implementation of Nimm for iOS. Nimm Game, a good illustration of the necessity of knowledge and mastery when failure must not be risked, however remote the probability of total loss may seem.